Hello, welcome to the 14th lecture in ML series. In this lecture, we will be introducing a new cost function for representing classification errors called cross entropy in the logistic regression settings, and how a gradient descent can be used to find the optimal parameters by considering this cross entropy cost function in the logistic regression settings. So let's quickly recap what we discussed in the previous lecture. As we have discussed, linear regression is not suitable for classification problems due to its unbounded output and it's sensitive to outliers. And we have introduced a new function called a sigmoid function which squashes the output from minus infinity to 0 to 1, which is helpful in uh, predicting probabilities. And we have defined a new hypothesis as a combination of the linear model and a sigmoid function, that is s theta of x as 1 by 1 plus e power minus theta transpose into x, where this s theta is defining the probability that output class 1 given x and parameters theta. Now, what is the cost function that we should choose? Now, we cannot directly choose a mean squared error. As you recall, we had used a mean squared error in the linear regression settings. We cannot use a directly mean squared error. The reason is, if we use this hypothesis function g of theta transpose into x, then it will become a non-convex function. That means it may have many local minima, and it is very difficult for a gradient descent to find a global minima. It may stuck in a bad local minima. So that is the reason we are not going to choose this mean squared error cost function. So let us see a new cost function. So what we need is, we need a cost function that must be a convex. That means it has a single global minima, and we should also penalize the predictions appropriately. So let us consider a simple example. You have a training example. You have a single training example, x comma y. Suppose the actual value of the given instance x is, or the actual class that it belongs to is class 1, and we want the hypothesis also to produce probability near to 1. If it gives near to 1, then the cost should be low, that the error should be low. Similarly, suppose if it gives a probability near to 0, then the cost should be high, something like infinity. Then what cost function is suitable? You can choose a cost function like minus log of h theta of x. So minus log of 0, so 0 you can write it as e power minus infinity, so then it will be infinity. So similarly, the other case, the actual class should be 0. We want our hypothesis to produce a probability that is near to 0. If it produces a probability near to 0, then the error should be low. And if it produces a value that is near to 1, then the error should be high, something like minus infinity. How are we going to get? We are going to use minus log of 1 minus s theta of x. Now, by combining these two, we can write the cost function in a compact form. That is what we call it as a cross entropy cost function. So the cost entropy function is minus y, because when y is 1, we need to use this cost function, minus log of h theta of x. When y is 0, we should use this cost function, that is minus log of 1 minus h theta of x. So by combining those two, so here y is the actual output that is required, and h theta of x is the predicted output. So you can see easily here, if y is 1, the second term is 0, and the first term is minus log of s theta of x, and it gives infinity if your hypothesis gives a value that is near to 0. Similarly, if for y is equal to 0, the first term will be 0, and the second term gives 1 minus 0, that is minus log of 1 minus h theta of x. So this gives a infinity if h theta gives a value near to 1. Okay, so this is a cost function that we are going to use, and the good news is this cost function is also a convex function. This is for one training example, and we are going to define the overall cost function by taking average over all training examples. So that is 1 by m sigma is equal to 1 to m minus y of I log h theta of xi minus 1 minus yi log of 1 minus h theta of xi, where I is representing the ith training example here. So as this cost function is convex, we can use gradient descent to find the global minima. That is, we can, for a given data set, we can find optimal parameters by using gradient descent. Okay, so to find that, we need a gradient. So that the gradient is dou by dou theta j of j of theta. So how are we going to calculate this gradient? So we just need to find a derivative of the. So let us consider a single training example. If you have a single training example, that is minus y log of h theta of x minus 1 minus y into log of 1 minus h theta of x. So as we know, this is h theta of x is our sigmoid function. So we will consider directly g of z, and also we know that z is theta transpose into x. So here we have to use a chain rule, because when you taking derivative with respect to theta j, z depends on theta and gz depends on z. So now dou by dou theta j of log of gz. So we will write with a chain rule. This is actually log, you consider it as a log x. Log x derivative is 1 by log x, that's why we get 1 by gz. Now dou gz by dou theta j. So as we know that gz depends on z and z depends on theta j. So we can write it as a chain rule, and we are going to get dou gz by dou z is g dash z, and dou z by dou theta z is simply xj, because z is theta naught plus theta 1 x1 plus theta 2 x2 so on theta j into xj. So all the remaining parameters are independent, so we will get xj here. Similarly, this log of 1 minus z, so it will be 1 by 1 minus gz, and dou by dou theta j 1 is 0, so we are going to get minus g dash of z into dou z by dou theta j. So dou z by dou theta j is again xj, and then if you simplify, and we also know from the differentiability in the previous lecture we had discussed, it has a nice property, g dash of z as gz into 1 minus gz. That means the derivative of the sigmoid function can be written with a same function. And we also discussed dou z by dou theta j is xj. So from that, if you substitute all, so we are going to get minus y into 1 by gz. Here g dash of z, we substituted gz into 1 minus gz, and assume that gz is not 0. So then we can cancel out these two terms. Then we are going to get minus y into 1 minus gz into xj. And similarly, if you simplify this, you are going to get 1 minus y into gz xj, because 1 minus xz, 1 minus g of z and 1 minus gz will cancel out. And we are going to get, and then you have a term here, y into gz into xz. Here you get minus y into gz into xz, so into xj. So these two will cancel out. We are going to get gz minus y into xj. So you know that g is the hypothesis, that is h theta of x minus y into xj. Now if you observe carefully, this h theta is the predicted probability value and y is the actual value. This is like an error, and it is multiplied with the corresponding x. Okay, so if you want for a training example, we have calculated for xy as an example. If you want for a single training example or a single ith training example, xi yi, then it will be h theta xi minus yi into xj of I. And it is over all training examples. When you consider over all training examples, dou by dou theta j of theta, then it will be 1 by m sigma I is equal to 1 to m h theta of xi minus yi into xj of I. So this is the gradient that we require in the gradient descent setup. And like that we calculate for every theta. And as you know that initially we take some random values for a theta, and then we'll update in every iteration by using this gradient, that is theta j is theta j minus alpha into dou by dou theta j of theta, and we repeat until we get a convergent solution. And if you observe carefully, this looks similar to the linear regression, and where alpha is where alpha is the learning rate, is similar to the gradient descent, because this also involves the same h theta of x minus y, where we have defined it as an error, and it is multiplied with xj. Only difference is the hypothesis. H theta of xi in the linear regression, that is theta transpose into xi. In the logistic regression, it is 1 by 1 plus e power minus theta into xi. Okay, so what is the summary? What we have discussed? We have a hypothesis function, that is h theta of x is g of theta of x, theta transpose x, and it outputs the probability between 0 and 1. And we have defined a new cost function called a binary cross entropy. We also call it as a log loss function, that is 1 by m into sigma I is equal to 1 to m minus yi into log of h theta of xi minus 1 minus yi into log of 1 minus h theta xi. And we can use a gradient descent to find an optimal parameters, and we had discussed how to update the parameters, and we'll be discussing in the next class how to practically implement this, and how to choose a decision boundary, and how it can be extended for a multi-class classification problems. Thank you.